For decades, researchers have attempted to better understand how data travels and interacts with environments, and how communication sources can be enhanced for the benefit of the warfighter. Current Air Force basic research pushes the boundaries of quantum physics and plasma chemistry, supporting designs for innovations in communications technology. At Hanscom Air Force Base outside Boston, Massachusetts, recently retired AFRL research scientist Dr. Edward Altshuler and his colleague Dr. Arthur Yajian developed a now patented and widely used design for very small super gain antennas.
There are a lot of people working on small antennas, electrically small antennas. We were the first ones to use a genetic algorithm to design these antennas.
Using this process, the researchers group a random combination of wires in an antenna, test their performance, and weed out the weak. This electrical survival of the fittest has resulted in extremely efficient antennas.
So we've designed a super gain antenna by feeding just one of the elements of that antenna in an end-fire configuration. We were able to use magnetic materials in a way to increase the bandwidth 50 to 100% beyond, again, what most people felt was impossible.
When achieved, super gain allows a small antenna to transmit over larger distances, and increased bandwidth allows more information to be transmitted. However, experience has shown that communications can get interrupted. To combat disruptions, plasma chemists at AFRL Space Vehicles Directorate are studying a variety of chemical interactions and reactions that appear in nature.
Historically, we've worked on the ionosphere, which is a charged part of the atmosphere that interacts with radio waves. We tried to understand the chemistry that might lead to understanding and possibly mitigating the effects of the plasma on reentry vehicles. Reentry vehicle will come into the atmosphere very fast, frictionally heat, and create a very dense plasma around it. That dense plasma then interacts with radio waves.
This plasma buildup can create radio signal blackouts, preventing communications with the ground and causing possible guidance errors.
The STAR team task is to study basically any plasma chemistry relevant to the Air Force or DoD or other national needs.
At Harvard University, Professor Lena Vestergaard Howe conducts revolutionary research on optical data transfer.
What we do is we cool atoms to, first of all, to really low temperatures. We use lasers to do that and create in our vacuum chamber the coldest place in the universe. We then send a laser beam in to illuminate that atom cloud. We call it the control laser. And we really use that to re-engineer the optical properties of that atom cloud. And once we have done that, we can send a light pulse in to the atom cloud and then slow that light pulse down to the speed of a bicycle. But we can do even more, because what we can also do is we can send a light pulse in, stop it and extinguish it in one part of space, and then regenerate the light pulse and send it back on its way in a completely different location.
With the light pulse converted to matter, the information contained on it can be stored or changed, presenting an entirely new way to manipulate the light pulses used in fiber optic communications. This AFOSR research could have a revolutionary impact on the future communications of our highly networked society. Learn more about U.S. Air Force-funded communications projects by visiting our websites, www.afrl.af.mil and www.afosr.af.mil. Like us on Facebook, watch us on YouTube, or follow us on Twitter.